In your next class, you're going to be doing a redox titration. And I'm going to review titrations, and specifically redox titrations, because it might have been a while. So we have a titrant in the burette, and we have a sample down here in the Erlenmeyer flask. Okay, so the sample is the thing we want to measure the concentration of. So we're looking for the concentration of that guy. So we need to know the volume, typically 10 milliliters because we measure it, but you're going to have to check your actual lab handout. And the titrant, well, typically we know the concentration of the titrant, right? Now it's going to be a slight problem in this lab. And we get the initial, and then the final volume, the exact amount needed to exactly neutralize our sample, and we have some kind of an indicator down in the sample that changes color exactly at the end point. And so we take final minus initial, and then we use basically volumetric stoichiometry to calculate the concentration of our sample. Now, there's a bit of a problem here. Okay, we actually don't know the concentration of our titrant. In this reaction, the titrant is I2 aqueous, iodine. And that is a very strong oxidizing agent, and it's going to oxidize our sample. At least it's better, otherwise the titration is a waste of time. But it's such a strong oxidizing agent, we don't know the concentration in advance. So we have to do this in 2 steps. The first thing we have to do is standardize the titrant. In other words, we have to measure the concentration of the iodine solution that we're using. It's not written on the bottle, unfortunately. And once we've done that, now how do you do that? Well, you do it by doing a titration. You start with a sample of known concentration, and then you add the titrant, and you do a number of tests until you get reliable results, and then you calculate the concentration. Okay, so once we found the concentration of our titrant, we're now going to go and do our actual titration. Okay, so you actually have to do 2 titrations. The first is measuring the concentration of the titrant, and then measuring the actual vitamin C in our orange juice. Now, I've got to be careful with the word juice. We take whatever we can buy cheaply at the store. So, all right. Let's go and review some of the things you'll have to do in advance of the lab. There's 2 things in particular. Now, the reaction is C6, H3O6. That's called ascorbic acid or a vitamin C. We are reacting with iodine. That's our titrant. And we are making this C6H6O6, which is aqueous, and we're going to get some iodide ions, also aqueous. So you need a balanced reaction to do the titration calculations. I'll set it up for you, but I won't do it for you. So this is the first one. And then the second one is involving iodine. So you've gone over how to do balanced redox reactions using half reactions. Quite straightforward doing these 2 half reactions. You should be able to put them together, and it's a fairly straightforward molar ratio. I won't tell you what it is, but it is. All right. The next part of the lab that you have to do, not in advance, but at the beginning of the lab, is you're going to have to calculate the actual concentration in our vitamin C, you see what we're doing here is we're going to see if you actually have enough vitamin C, just like they say in the label. So I'm going to go through the calculations, and this is, hopefully you've seen these before. A nutrition facts label has to be on all commercial food products. And you're going to need the serving size in milliliters. And you're going to have to know how much vitamin C is in there. And this is in a percentage. So what does that mean? Well, we're going to be calculating the concentration in moles per liter. Okay, so I need the moles and I need the volume. Well, the volume is 1 serving. In this case, it is 240 milliliters, which is that number of liters. Okay, now the number of moles, a little tricky. The first thing I'm going to do is figure out the mass. How do I do that? Well, I get 90% of my vitamin C from 1 serving. And we tell you this in the lab, so it's no big secret. The recommended daily allowance of vitamin C is 60 milligrams. So if I do this, I will get 54 milligrams. Unfortunately, I want moles. Well, I'm going to need the molar mass. And you're going to need the formula. It is C6H3O6. Well, why don't you figure that out? I'm hoping you got the same thing as me. Okay, so let's go through the math now. I need to get the number of moles. Number of moles is mass divided by molar mass. Now watch out, the units are a little tricky. I need to use grams, not milligrams. So you will discover it's a tiny amount of vitamin C, which is good because, I don't know, it just is. I'm going to add a few extra digits. It's 10 to the minus 4 moles. Okay, to get the concentration. Well, I got the moles, I got the volume. It's quite straightforward. So it is the number of moles divided by the volume. And it's going to come out in moles per liter. Well, let's just do this, and then we'll adjust the answer to make it more reasonable. So you don't get very many moles per liter. I'm going to go with 2 significant digits. But we're going to go with millimoles per liter, because that's much more reasonable, and it's 1.3 millimoles per liter. So if this contains 90% of your vitamin C, it should have and you drink 240 mils, you should get 1.3 millimoles per liter. That should be the concentration. Okay, now you can't do this in advance because I don't know the nutrition facts label of your sample. We're going to buy whatever's on sale. And so I guarantee it won't be this number. So I'll see you in class.